Good morning, team. Are you ready for video number 10 in our chemical reactions journey? Even though we've kind of diverted off our path to look at concentration units because we need those in order to complete our stoichiometry calculations. Because if we're given solutions, we need to extract out the amount of solute in there. To do that, we need concentration, and there's so many of them. So I can almost do solutions as a whole separate module in itself, but it's kind of a transition between our introduction to chemical reactions and stoichiometry, and then where we're going to be headed, chemical reactions that occur in aqueous solutions. So precipitation reactions, acid-base reactions, getting into some meat and potatoes, my friends. So we looked at molarity last time, so I'm going to just slowly introduce the different types of common concentration units you might run into, how to use those as conversion factors, right, between solution amount and solute amount, depending on the units and the definitions. And then we'll look at making solutions in a whole completely separate video once we look at all the different types of concentration units. And again, we're not even covering all of them. It gets crazy. Let's look at, to me, the most common sense concentration unit, the percent concentrations. And there's three we're going to look at based on percent of what? What are we looking at? Solution, solute? Are we looking at mass? Are we looking at volume? How do you define the amount? Because remember, we're looking at concentrations as the amount of solute over the amount of solution. What those units are determines the type of unit of concentration: molarity, normality, mass percent. So the percent one is just a ratio. Again, we learned early on in this semester how to look at percentages as conversion factors in chemistry. And there's two ways we can look at percents, right? We can look at it as any concentration unit, a part over whole, right? That's all it is. So the whole being defined as the solution and the part being defined as the solute. Remember, solution is the solute plus the solvent. So we're interested in some certain part over some certain whole. And specifically, percent is parts per hundred, right? I mean, we learned growing up, if you have 100 marbles and 15 of them are purple, well, 15 out of 100 would be 15%. And we tend to think of that as 0.15. But as a chemist, we need to put what that is. 0.15 doesn't work. It doesn't give us enough information. What over what? What's the part? What's the whole? Right? What are the units? Are they grams? Are they milliliters? Are they liters? Are they moles? So there's more information we need as a chemist. We can't just think of percents like we did in 10th grade as 0.15. For example, 7.3% to a chemist is a parts per hundred, 7.3 over 100. And what we're going to do based on the percent unit concentrations, we're going to define 7.3 what of solute, right? Would that be grams, milliliters, moles, whatever? And on the bottom, we'll define as 100 parts of solution. So 7.3 parts of the solute, 100 parts of the solution. We're going to define it as parts per 100. And we just have to put whatever units we have there. So there's going to be three types of percent concentrations we're going to look at. And then we'll do mole percent next semester. It's not important right now. But let me list those up on the board. Hopefully they make common sense. At least for me, these concentration units made the most common sense to me. Molarity took a while to get used to. Normality, I don't think we ever get used to that. Let me put these up on the next board. Here is a look at the only 3% concentration units we're going to focus on, from the most common to the least common for us. Depends on what industry. Do you work in academia? Do you work at some chemical manufacturing plant? The languages used, do you work in medicine? The languages of units are different for each one because they're appropriate for that field. Probably the most common one you're going to see in academia for us, other than molarity, will be mass percent, or in industry you'll hear it called weight percent. So you see this little W over W percent. So that is the weight or mass of the solute, the part, over the weight or mass of the solution. If you take that ratio, times it by 100, you get the mass percent. So very easy to calculate mass percent concentrations. All you got to do is take the information provided, figure out how many grams of solute you have, how many grams of solution you have. But watch out. Be very, 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 very careful. A lot of people make this mistake and they insert the grams of the solvent there. Remember, grams of solution is grams of solute plus grams of solvent. Right? You got to take the mass of the solute and add the mass of the solvent to get the mass of the solution. Ran out of space there, but you get the point. So it can be a little more involved sometimes. You can get some crazy questions with that. We're going to look at how to use that as a conversion factor most, at least in my classes. How do we convert from solution to solvent? Solute. So as long as we know the mass of the solution, we can get to the mass of the solute. Just like with molarity, if we knew the liters of the solution, we could get to the moles of the solute. No big deal. Or vice versa, if we know the mass of the solute, we can figure out the mass of the solution just by assuming 100 grams on the bottom. All right, in the same way of thinking, we could do the volume percent. All you're doing is switching the units from grams to milliliters. So you'll see that called volume percent or VV percent, and that is the milliliters of solute over milliliters of solution. And again, the volume, the milliliters of solution will be the milliliters of the solute plus the milliliters of the solvent. And really, you could put, as long as the two mass units are the same and the two volume units are the same, you could do liters over liters, pounds over pounds. It would all work as long as that ratio is good. And the one that's I don't see as much, it's more industrial, I see it with like bleaches and things like that, is mass volume percent, or you'll hear in industry weight volume. You'll see the W over V. So industry, you see WWVV and WV. Whereas in colleges, you'll see mass percent, volume percent, and mass volume percent. Very rare for me to use this one. And that one, you're just taking the amount of solute as the mass in grams, and the volume of the solution in milliliters. Take that ratio, times it by 100, you've got the percent. So pretty simple to calculate the concentrations of solutions. So you can do some of that in the homework. I'm going to let's do maybe a couple examples. Maybe the mass percent, that's the most common one we're going to use, and maybe a mass volume percent one. To look, we'll start with an easy one, maybe with mass volume percent, and then a more complicated one with the mass percent, and how to use those in a stoichiometric calculation unit line equation, which is the focus of this particular journey we're on, this particular chapter with stoichiometry and all that good stuff. So let's start with an easy example on how to use percent concentration units. Let's see how you do on this this first baby step. Right? And again, we've dealt with percents before, so it's no different. I want you to be a procedural thinker. Less memorization, more procedures. What's a percent? Parts per 100. Assume 100 parts a whole, and then what's the parts, of the portion of that whole we're interested in. So we've got some sodium hypochlorite. I think that's a common active ingredient in some bleaches. So we want how many milligrams of that active ingredient is in 4.54 milliliters of a bleach solution. Okay, so bleach is the whole, that's your solution, and the NaOCl, the sodium hypochlorite, is the part, the solute. And the concentration of that bleach solution is 5.1 weight volume percent. So how are we going to set this up? You don't have to write this down, but I want you to think about it this way. That 5.1% means there's 5.1 grams of the part, the solute, the sodium hypochlorite. Remember, a percent's parts per 100, so we're assuming 100 parts of the whole. But what's the whole? The bleach. You could call it solution or bleach. And its volume, so that will be milliliters of bleach. That is how I want you to think about percent concentration units. Go, oh, that number over 100, and if it says mass or weight, put grams. If it says volume, put milliliters. Wada bing, wada boom. All right, that's our ratio. That allows us to convert from bleach units of milliliters to solute units, in this case, specifically sodium hypochlorite units of grams. That'll be our, now I'm not going to start with that. That's a conversion factor. I want to look at, I'm solving for solute, so I want to start with the solution. So here's my game plan. We're going to go milliliters of bleach, which is our solution, correct? I'm going to, and I'm in milliliters. If I wasn't in milliliters, I'd have to convert to milliliters, right? Because that's the unit here. So I can go from milliliters of bleach to grams of the solute, right? Using this as a conversion factor, a pretty simple setup. And I was a booger head and I did milligrams. So this is just a two-step problem. Very, very easy to do. Let's pop this out. Let's do it in whatever, I don't know what color that is, but let's do it. We got what, 4.54? So 4.54 milliliters of bleach, or you could say solution. Let's just pop that right down. So for every 100 milliliters of bleach, there are 5.1 grams of whatever that solute is. Hopefully that's no big deal. But that's how we're going to use our brains to think about percents. And that cancels out solution units. We've now successfully gone from a whole to part, solution to solute. And then I asked for milligrams. So there's 1,000 milligrams per gram. And you could put NaOCl on there if you wanted to. I'm just running out of space. And I can now cancel out grams. So I've got 3 significant digits in my starting volume of the bleach. That 100 is exact. It's a defined value. The 5.1 is not, though. Remember, concentrations are not exact values. So I got 2 significant digits there. Metric conversions are exact. So I'm limited to 2 significant digits because I'm doing all multiplication division. So 4.54 times 5.1 divided by 100 times 1,000 divided by 1. You can do that in your head. Boom! What do you get? I pop this out. 231.5 milligrams, but we're good to 2 significant figures, right? So that 2 and a 3. So let's pop a vertical line after the 3. And we got to go, is that closer to 230 milligrams or 240, right? This first non-significant digit is less than 5, which means we're not going to round up, so we're closer to 230. So we're going to go 230 milligrams of NaOCl. Wada bing, wada boom, drop my pen! Got to keep that trailing non-significant 0 to keep the magnitude correct. Not a big deal. Let's do a harder one now. Yay! This is what I would call a challenge problem for first semester general chemistry. This is about as hard as it's going to get. It's going to take pretty much most of the concepts we've been studying all semester long, putting them into one fell swoop. Oh, Coach loves those problems on exams, right? Chemistry just builds on itself. Although the only really new thing here is the mass percent. Right? So let's think about this problem. A lot of information. There's no way I have room to do this on the board. I'll have to solve it. So let's set up the game plan. Let's think about it. If it's getting to the point where your head's going, mama, call the ambulance, and you really don't even know how to start. I get that a lot. They're like, I don't even know how to start the problem. Well, that means you're not thinking correctly, all right? Or you haven't been doing your homework, one of the two. If you can't start the problem, read through it. Don't try to solve it. Don't look at any of the numbers. The numbers don't matter. Focus on the unit line equation. What species are you solving for and what units? Extract that information out of it. That goes over here. Then you go, what species am I starting with and what units? That goes over here. Get the endpoints, like doing a puzzle. Get the straight edges around, and then you can fill all those things. I was just doing that with my 8-year-old son, doing some really hard puzzles. It gets easier and faster the more pieces you get in there, right? But you got to define the boundaries first. So define your starting species and unit and your ending species and unit, and then look at the conversion factors that allow you to go from one species to another species and one unit to another. Are you going mass to volume? That's density. Are you going solution to solute? That's concentration. Are you going from one metric unit to another, or an English unit to a metric unit? Find those exact conversion factors that you can find. Or maybe there's a specific one that's provided for that one problem. Well, let's take a look at it. Let's do our game plan. And once I get this game plan down, I want you to pause it and try to work it out on your own first, and then compare to what I have. So here's our starting point. There's our very ugly endpoint. I got a D in penmanship, so whatever. don't even think you have to take penmanship anymore in grade school. It was atrocious in penmanship. Plus, I had focus issues. If you haven't figured that out by now, I have serious focus issues. But like I said, it's 30, 40 years ago I was in school. 40 years? Oh, 40 years ago. Over 40 years ago I was in grade school. We didn't take as much medicine. Different world, right? Here we go. I'm going to go through this big gobbledygook of mess and try to figure out what I'm solving for. Now, I was nice and gave you a balanced chemical equation. We've got some zirconium solid. Popping that into some phosphoric acid, it looks like. Forming nice bubbles of hydrogen gas. We can collect and explode. And some zirconium 2-phosphate, it looks like. We'll learn how to predict states in the next chapter. That's not important. So I'm giving you this. Although next chapter, we're going to learn how, the point is to take out the mathematics and learn how to predict the products. Hey! So how many milliliters of a 65% by mass solution of phosphoric acid with a density of 1.52 grams per milliliter solution? So we've got a phosphoric acid solution. That's this. And we're given a lot of information on that. We're giving the density of this, and we're giving the concentration of that as a mass percent. So that'd be 65 grams of H3PO4 over 100 grams of the solution. We're solving for that. All right. So I want milliliters of the phosphoric acid solution. I can't get my oxygen. That's what I'm solving for, right? Given two conversion factors. One that allows me to go solute to solution, one that allows me to go mass of that solution to volume of that solution, or vice versa. How many are required to react with zirconium solid? Given no information on the zirconium solid, so I'm just going to make the assumption I have exactly the right stoichiometric ratio or proportion of that, or excess. So the phosphoric acid will be my limiting reactant. Remember that H3PO4 molecules, solute molecules, are what's reacting, not the water. Not the solution doesn't react. The solute in it reacts. To produce 4.8 grams of hydrogen gas. So this is what I'm starting with. So I'm going to take the grams of hydrogen gas right here. And I've got to get from hydrogen gas to phosphoric acid solution in a very succinct way, following the units. So I'm going to be going from here. Now remember, when you're doing stoichiometry, that's moles. So take whatever's provided here, get to moles. Can we get grams of hydrogen to moles? It's a molar mass. That should be pretty straightforward. So we can go to moles of H2 quite easily with the molar mass. And then we can go 3 moles of hydrogen to 2 moles of phosphoric acid. And this is the solute, my friends, not the AQ. That is the solute, the particles moving around in the solution. But I want to know how much solution there is. So I need something. So this is molar mass. This will be the stoichiometric ratio to get from here to here. Now I got to get to solute to solution. But I was given a 65% by mass, which means that's grams of H3PO4 over grams, 100 grams of the solution. So 65 over 100. I need to get to grams of solute, and then I can go 65 grams of solute to 100 grams of solution. So I got to get moles of H3PO4 to grams of H3PO4. And this is the solute still. This is where students get confused. This is much harder than the other one. Now, if I'd given you molarity, we could have just gone straight from moles of H3O4 to liters of solution. But I didn't give you molarity. I gave you mass percent. That makes it one step more difficult. And I went to grams of H3PO4 because that's the units in the mass percent concentration. So I can now go from grams of H3PO4 to grams of solution using that concentration unit. And that will go, I don't have enough room here. This will go to grams of the solution, right? This is a harder problem than I thought. So grams of H2, that's my first, notice I'm going backwards here. Grams of my product to moles of my product, back to moles of my reactant, the solute, to grams of that solute, to grams of the phosphoric acid solution, because I gave you mass percent, and then I can go grams to milliliters of solution using the density. So 1, 2, 3, 4, 5. That's a 5-step problem. And the only new step is this one right here. Using the mass percent to go solute to solution. Pause the video. Do that very carefully. Cross out the units in the unit line equation. Track your uncertainty. And see how many milliliters of phosphoric acid solution we need to get 4.8 grams of hydrogen gas. Let's see if we get the same rounded value. Track your units. So I'm going to pause it, erase this board, and I'm going to write the whole thing out, and then we'll walk through step by step. I decided to walk through it with you. This is, let's take it one step at a time. So I just kind of simplified the board and give myself some room. So I rewrote the balanced chemical equation that was provided for you. I summarized the information on the phosphoric acid solution, 65% by mass. Density is 1.52 grams per milliliter. And then I put our game plan back up with our 5 steps. So let's go ahead and start. Let's take our starting mass. I think that was 4.8 grams of hydrogen. Let's write that down. So 4.8 grams. That's our starting point. This is what species, what units. We got to get to moles so we can get from moles of hydrogen of what we started with to moles of what we're interested in. So hydrogen, what's that? 1.00794. 1.00794 times 2, or actually 1.00794 plus 1.00794. So I get 2.01588. 2.01588 grams of hydrogen. Can you tell I like forming hydrogen? And so the grams of hydrogen cancel out. Boom, boom, I'm now in moles. I'm not going to fit this on one board, so I'm going to have to go over and then cycle down and do a second row. But I want you to do it all in one connected chain on your paper because you have more space than I do. Check. Step 1. That's all dimensional analysis is. It's just one link at a time, one step at a time. Each step is not particularly challenging, but when you put them all together, you're like, whoa, look what I did. That was a tough one. There's really not hard or easy problems, just longer and shorter problems if you do it correctly with unit line equations. Let's convert. We're now in moles. Let's go to moles of this, 3:2 ratio. So there are 3 moles of hydrogen produced for every 2 moles of H3PO4 molecules. All right. 2. Whoops, I almost forgot my unit there. There we go. So there's our 2:3 ratio, and check. Step 2, our stoichiometric factor. We're now in terms of the solute. Now our goal is to get from solute to solution. That's where we're going to need the 65% by mass, right? And since that's grams, right? So we're going to look at the 65% by mass as 65 grams over 100 grams of solution. That's pretty squishy up there, but that's 65 grams of solute over 100 grams of solution, the solute being H3PO4. So let's just convert this to grams, and then we're after it. So I'm going to cross out my moles of hydrogen there. So let's get the molar mass of H3PO4. Oh, there's going to be a doozer. So we got 3 hydrogens, so take 1.00794 times 3. That's good too. 1, 2, 3, 4, 5 decimal places. We've got a phosphorus. What's that? 30.973761. Who got so many decimal places there? My goodness. So we got 1 of those. So 3 hydrogens. 3 of those. 1 phosphorus. And 4 oxygens. So 15.9994 times 4. Looks like we're limited to 4 decimal places. So 3 hydrogens, 1 phosphorus, 4 oxygens, limited by the oxygens to 4 decimal places. So you should get 97 something. So I get 97.9951. There's my 4 decimal places. Then carry on 2 more digits. we get an 81 grams of H3PO4. That's the solute, right? Per mole of H3PO4. Check. I'm already out of space, my friends. So I'm going to bring that down. Imagine this going across in one line. Now I'm in grams of solute. So I can now pull out my mass percent concentration to go from solute to solution. So this tells me there are 65 grams of solute for every 100 grams of that phosphoric acid solution. This is where a lot of students get confused, because if you don't do the species in units, they end up just multiplying by 0.65. You're not, right? We're dividing by that. So students get things up. So I know if they're not thinking correctly, they get it upside down. If you track your units, what's the solution, what's the solute, you don't get it upside down, right? Depends on which way you're going. Are you going solution to solute or solute to solution? One way's this way and the other way's flipped. We have now successfully gotten to the grams of the solution, but I asked for the milliliters of the solution, right? That's why whenever you see density, you know you got to do that. So we know there are, 1.52? 1.52 grams of solution per milliliter of solution. So moles of solute cancel, grams of solute cancel, grams of solution cancel. And the only thing I got left in the numerator is milliliters of solution. Yay! Check. This is a hard problem, guys. If you can handle this, you're good. All multiplication division, 2 sig figs, 1, 2, 3, 4, 5, 6, exact, 6, exact, 2, 3. So I'm limited to 2 sig figs here in the mass and the concentration. So calculate that out. I get 157.4. Good to 2 significant digits. Is that closer to 150 or 160? Well, that's higher than 5, so it's going to round it up. So it's closer to 160, right? Hopefully I did my calculations correctly. Double check me and email me if I'm wrong. I'd hate to do this video all over again. So about 160, really, you can measure out 157.4 milliliters if you want to produce 4.8 grams of hydrogen, assuming it's a perfect reaction in lab, of course, and you get 100% yield. That's percent units for you, my friends. Whew, I think that was the tough one.